welcome to the beautiful campus of Johns Hopkins University, where we will be hosting the 2018 Miss Molecule competition. Today's hosts are me, Noelle, and Steven. Now we're going to go over to Steven to talk about the logistics of this competition.
Thank you very much. So now let's move on to talk about the logistics of this competition. This year we have 13 candidates will be introduced later on. And this competition is judged by 3 well-known experts. First, right here we have James Gordon from the United States, and next we have the Oprah Winfrey from the United States as well. And lastly, we have Simon Cowell from the United Kingdom. And then this year, the grading category will be broken down into the beauty of the molecules, the symmetry of the molecules, and the application of each examples. By the end of the competition, we'll have 3 winners, and then they will be awarded by coloring. And then now, let's move on to introduce to you to the contestants.
And for our contestants, we have Ava from Ames, Bella from Bloomberg, Claire from Chemistry Building, Grace from Gilman, Megan from Maryland, Sarah from Schreiber, Holly from Hodson, Lisa from Levering, Kate from Krieger, Ella from Eisenhower, Rose from Remsen, Jennifer from Jenkins, and finally Wendy from Woolman.
So this year's competition is based on the VSEPR Theory, which is the valence shell electron pair repulsion. This can define the electron groups which are the possible spots for bonding. And then we have the electron groups geometry and the molecular group geometry. Hang on a second, they look so similar to each other, and what is the difference?
Hey Steven, let me answer that question for you. So the electron group geometry is going to be based on the electron groups which you previously defined as spots available to bond. So in this tetrahedral, there is 4 possible spots to bond. And in this one, all 4 are used. So both the electron geometry and the molecular geometry is a tetrahedral. In this case though, there is still 4 spots to bond. So the electron group is still a tetrahedral. However, there's 2 lone pairs, meaning the molecular group geometry has now changed. The molecular group geometry is now going to be bent due to the 2 lone pairs that take up the spot of a bonding pair.
So now I see the difference. Let's move on. Next thing up is the bond angle. What the bond angle is that it is the angle between the terminal atoms, the central atoms, and the other terminal atoms. So it is basically the angle right over here. Next up is the hybridization. What it is that it's actually the mixing of atomic orbitals in order to allow for bonding. But then what does that actually mean?
Well, hybridization is a really tricky topic, so we're going to try to simplify it. So let's take the molecule CH4, and let's go ahead and draw the Lewis structure for it first. So we have a carbon as a central atom and 4 terminal hydrogen atoms bonded to it. This is an example of a tetrahedral. Now, carbon's electron configuration is 1s2, 2s2, 2p2, where these are the valence electrons that we use for bonding. So if we move over here, we're going to draw out the electron energy diagram for carbon. So this is energy, and we're just going to draw out the one for the valence electrons. So we have 2s and 2p, and we're going to go ahead and fill in the electrons that carbon has as valence electrons. So 1, 2, 3, 4. So in this setup, carbon can only make 2 bonds because there's only 2 places where electrons can pair. But obviously, according to this molecule, it can make 4. So how do we do that? Well, in order to do that, we need to move this electron to this empty orbital. But they're at different energy levels. So in order to do that, we're going to mix the atomic orbitals and create 4 sp3 orbitals, and we'll put the electrons in them. So it's 1, 2, 3, 4, which now allow for 4 separate bonds at the same energy level.
So now that we have learned all the basics, let's move on to how we can decide on what the molecular geometry of each molecule is. Let's start with a very easy example of water, which is H2O. And then the first step is to draw the Lewis structure, which can be drawn as the central atom as an O, and then we have 2 hydrogen on each side, and then we have the bond here, and then along with the lone pair. So after we have the Lewis structure, we want to determine the electron groups around the central atoms, which is 1, 2, 3, and 4. And right here, we can see there are 2 lone pairs. So we can tell that the structure is a bent structure for water. And then the similar theory goes on to all the other molecules to decide on the geometry. Enough chemistry for now. Let's get the show started.
This is Ava. She has 2 electron groups in 0 lone pairs, making both her electron group geometry and molecular group geometry linear. Her bond angle is 180 degrees and her hybridization is sp2. One use of Ava is for BeCl2, which is a raw material for electrolysis and a catalyst for Friedel-Crafts reactions.
So next up we have Bella. Bella has 3 electron groups in 0 lone pairs. Both of the molecular geometry and the electron group geometry is trigonoplanar for Bella. And then as you can see, the bond angle is 120 degrees, and she also has the sp2 hybridization. One of the common example for the trigonoplanar geometry is the BF3. And one of the uses of them is that it is a colorless toxic gas in moist air. And another one being it's a useful Lewis acid as a building block for other boron compounds. There you go, Bella.
And next up we have Claire. She also has 3 electron groups in 1 lone pair, making her electron group geometry trigonoplanar, but her molecular group geometry is bent. Her bond angles are now less than 120 degrees, and her hybridization is still sp2. And let's go ahead and talk about an example, which is SO2. It is a preservative in food, which helps to maintain the color of the fruit.
So now let's talk about Grace. Grace has 4 electron groups with 0 lone pairs, and both of her molecular geometry and the electron group geometry are tetrahedral, which means that she has the bond angle of 109.5 degrees. She also has a sp3 hybridization, and one of the common example is the CH4, which is very useful for the testing of gas appliances, which are to be used for natural gas areas.
Next up we have Megan. Megan has 4 electron groups and 1 lone pair, so her electron group geometry is tetrahedral, while her molecular group geometry is trigonal pyramidal. Her bond angles are slightly less than 109.5 degrees, and she has an sp3 hybridization. Now, one common use of Megan can be NH3, which is a refrigerant gas for the purification of water supplies and also used as a household cleaning.
Now we have Sarah. Sarah has 4 electron groups and 2 lone pairs. It has tetrahedral as its electron group geometry and bent as its molecular geometry. It also has the less than 109.5 degree as its bond angle, and also has a sp3 hybridization. One of the common example is water, H2O, as you can see as the Lewis diagram. And there's all these use of water as we're here, we're alive. So let's keep going.
And this is Holly. She has 5 electron groups and 0 lone pairs, making both her electron group geometry and molecular group geometry trigonal bipyramidal. Also, her bond angles are 120 degrees and also 90 degrees. Her hybridization is sp3d, and one common use of Holly is PCl5, which is a starting material for the synthesis of phosphorus compounds that can be used for pesticides and other chemicals.
This is Lisa. Lisa has 5 electron groups and 1 lone pair. She has trigonal bipyramidal as her electron group geometry, and she has seesaw as her molecular geometry. She has less than 120 degree as the bond angle, and also less than 90 degree for the bond angle. She has the sp3d hybridization, and one of the common example is SF4. It can be used as a liquid crystal material medicine, and it can also be used as an oil repellent.
And this is Kate. She has 5 electron groups and 2 lone pairs, making her electron group geometry trigonal bipyramidal, while her molecular geometry is T-shaped. All of her bond angles are less than 90 degrees, and her hybridization is sp3d. Now, for use for Kate is ClF3, and that is used in nuclear reactor fuel processing and also in the semiconductor industry.
This is Ella. She has 5 electron groups and 3 lone pairs. She has trigonal bipyramidal as her electron group geometry, and she also has a linear molecular geometry. She has the 180 as the bond angle, and she has a sp3d hybridization. One common example is the XeF2. One of the use is that it can be decomposed on contact with light and water vapor. Another use is that it can be used as a fluorinating agent.
This is Rose. She has 6 electron groups and 0 lone pairs, making both her electron group geometry and her molecular group geometry octahedral. Her bond angles are all 90 degrees and her hybridization sp3d2. One common use of Rose is SF6, which is a test gas in respiratory physiology and a contrast agent for ultrasound.
This is Jennifer. She has 6 electron groups and 1 lone pair. She has the octahedral electron group geometry and the square pyramidal molecular geometry. She has less than 90 degree bond angle and she has an sp3d2 hybridization. One of the common examples is the BRF5. It can be used as the extraction of oxygen, which makes it useful for oxygen isotope analysis.
Last but not least, we have Wendy. She has 6 electron groups and 2 lone pairs, making her electron group geometry octahedral, while her molecular group geometry is square planar. Her bond angles are all 90 degrees and her hybridization is sp3d2. One example of Wendy is XeF4, which is a decomposition agent of silicon rubber in order to find trace metal impurities. Thank you for meeting all of our contestants this afternoon.
So now we have seen all the contestants, let's leave to the judges to decide. This is the moment. Let's see the results. Here you go. Drum roll, please. Let's starting from the 3rd place. We have Rose. The reason she got elected is because she has great use for the ultrasound. And then next up, 2nd place. Drum roll. Sarah! Woo! Which is water. Of course it's water. I mean, it makes sense it's 2nd place. Now, it's the final time. The 1st place, Grace. Of course it was Grace. Congratulations. Here you go. 1st place, 2nd place, and 3rd place.
We would like to thank everyone for coming out to Johns Hopkins University today in order to watch the Miss Molecule competition. Goodbye.
The shape of you.